Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program explores the basics of powder metallurgy. Powder metallurgy is a metalworking technology used primarily for producing parts from metal powder. Powder metallurgy is also used to make ingot and billet for subsequent reduction into bar, plate, sheet, and other metal forms. Powder metallurgy dates back thousands of years and is a viable alternative to the use of cast and wrought metals. It is widely used to make a great variety of parts, such as gears, cams, casings, bushings, and fasteners. These parts are then used in automobiles, appliances, computers, electrical and magnetic devices, cameras, power tools, aircraft components, and much more. The primary advantage of powder metal parts is design flexibility. Parts can be produced to high density for maximum structural performance, or to controlled porosity for applications such as filters and self-lubricating bearings. Another advantage is the ability to produce parts that are close to their final shape. This is known as net or near-net shape forming. The benefits of net or near-net forming are the reduction or elimination of secondary manufacturing operations, conserving metal, and reducing costs. Metal powders for parts production are available in numerous types and grades to meet a wide range of specifications and performance requirements. These metal powders include iron and steel, which are the most common, along with copper, aluminum, nickel, cobalt, molybdenum, tungsten, tungsten carbide, titanium, tantalum, magnesium, and others. Metal powders are produced by physical or mechanical methods. Atomization is the most common physical method. It involves breaking up a stream of molten metal with a jet of high-pressure water or inert gas, such as nitrogen or argon. Resultant droplets solidify and settle as powder particles at the bottom of a tank and are collected. Water-atomized particles tend to be irregular in shape, and gas-atomized particles are more spherical. Other atomization techniques include vacuum or soluble gas atomizing, the rotating electrode process, which uses helium as the inert gas, and several rapid solidification processes. Mechanical methods of producing metal powders include milling in either hammer, rod, ball, grinding, or attrition mills. These mechanical methods are used mainly to reduce particle size of hard and brittle powders, such as oxide powders, or for alloying, blending, and work hardening. Metal powders used for parts production can be a combination of various elemental particles or pre-alloyed powder. If elemental powder is used, each of the ingredients that will comprise the desired part are mixed in proper proportion into a uniform blend. With pre-alloyed powder, the proper proportion of ingredients is already present in each particle. In either case, additives such as binders and lubricants are usually added. The powder is then consolidated in molds or dies, shaping and densifying it into a compact of the desired part. At this point, the part, or compact, is in a green state, where the powder particles are just lightly joined together. In this state, the parts have a so-called green strength, which is usually only sufficient for handling purposes. The parts are then transferred to a sintering furnace. During sintering, parts are heated at a temperature below the melting point or range of the base metal, but high enough to metallurgically bond the individual particles. Sintering further densifies the parts, increasing strength. Final part density is extremely important. Although controlled porosity is required and achievable for certain parts, the performance of structural parts increases directly with increasing density. The common methods of consolidating and shaping metal powder for parts production include mechanical pressing, injection molding, and isostatic pressing. Most parts are made by mechanical pressing and sintering. Parts are usually small to moderate in size and can be simple or complex in shape. They can be very thin or thick and can also have one or more levels, shallow or deep holes, and various other details. Parts produced by mechanical pressing can be net or near net in shape and have very close tolerances. Part production rates are high, from several hundred to thousands of parts per hour. In mechanical pressing, the powder is automatically gravity-fed into the die of a mechanical or hydraulic press and consolidated to a specific density. Pressures of 10 to 60 tons per square inch are created by the vertical action of an upper punch or by the double action of an upper and lower punch. Pressing is typically at room temperature, although elevated temperatures can also be used. Core rods are used inside the die to control formation of holes parallel to the direction of pressing. If the part being made is thin and uniform in height, the powder can be pressed from one side by the upper punch. When that punch withdraws, a lower punch raises the part out of the die. The part is then ejected by the wiping action of the powder feed chute, which also wipes powder for the next piece into the die. Ejection from the press can also be accomplished using automated handling equipment. The density of pressed powder tends to decrease along part height as the distance between the compacting punch and die increases. To produce more uniform density, thick parts are compacted by a set of upper and lower punches. After pressing, parts are transferred to the sintering furnace. Sintering furnaces include preheat, high heat sintering, and cool-down zones, each having a controlled atmosphere. Depending on the base metal of the part, the atmosphere of the sintering furnace may be endothermic, which is composed mainly of hydrogen, nitrogen, and carbon monoxide; exothermic, which is composed of nitrogen mainly; dissociated ammonia, which is hydrogen and nitrogen; or entirely hydrogen, vacuum, or inert gas. To ensure proper sintering, the heating rate, maximum sintering temperature, time at the sintering temperature, cooling rate, and furnace atmosphere must be closely controlled. After sintering, parts may require additional processing in secondary operations to achieve net shape and/or meet performance requirements. Secondary operations include repressing, forging, sealing, machining, heat treating, steam treating, plating, and joining. Repressing is occasionally used when mechanical pressing and sintering do not yield sufficient density to meet the part's required performance. Repressing is also used to coin or size parts to close tolerances. Repressing, which can be done at room or elevated temperatures, usually requires additional tooling. The part may have to be annealed or softened first, or sinter annealed during sintering. Forging refers to hot forming a preform that has been partially shaped and densified by mechanical pressing or sometimes isostatic pressing. Forging can provide both vertical and lateral metal deformation. It is used to increase density and provide more complex or net shapes than can be achieved by mechanical pressing and sintering alone. Density can approach full or theoretical density. Forging can also refine a part's grain structure, improving its structural performance. Most forgings are alloy steel. They are used extensively in the aerospace and auto industry for various parts. Part porosity can be eliminated or substantially reduced by impregnating or sealing a part with a polymer resin or a metal having a lower melting point than that of the part base metal. Copper is commonly used for iron parts. Copper slugs are placed on the parts and passed back through the sintering furnace. The copper melts and infiltrates the pores and, on cooling, solidifies. Secondary machining operations are needed because side details, such as grooves and holes that are transverse to the pressing direction, are impossible to produce by the vertical action of mechanical pressing. These machining operations include turning, milling, grinding, drilling, and tapping. Choosing the proper coolant is extremely important when machining powder metal parts, especially for porous parts because the coolant may be absorbed and react with the base metal. Heat treating is used to modify a part's properties. Surface hardening increases wear resistance while maintaining toughness at the part's core. Through hardening increases overall strength and other mechanical properties. Steam treating develops an oxide surface coating, which increases wear resistance mainly, but also the strength and rigidity of ferrous parts. In addition, steam treating reduces some internal porosity and all surface porosity. Conventional plating methods can be used on powder metal parts, but porous parts must be sealed first to provide non-porous surfaces and prevent entrapment of plating solutions. Joining processes include mechanical fastening, brazing, soldering, and numerous welding methods. Most of these secondary operations are also applicable to powder metal parts made by injection molding or isostatic pressing. Injection molding of metal powder is used to produce very complex and intricate parts. Holes in almost any direction, undercuts, threads, and other details can be molded, markedly reducing or eliminating the need for subsequent machining. Parts produced by injection molding typically are small, but their density is high, usually 95% or greater. Common metals used for injection molding include iron-nickel-copper alloys, iron-silicon alloys, some alloy and stainless steels, and special electrical and magnetic alloys. Overall, injection molding involves powder mixing, injection molding, debinding, and sintering. The powder is mixed with a thermoplastic binder at an elevated temperature, then hardened by cooling to room temperature and granulated to produce the feedstock for molding. The feedstock is heated in the feed barrel of an injection molding machine. Once it reaches temperature, the feedstock is injected into a mold, which may have one or multiple cavities of the part to be produced. Being in the green state as molded, the part is allowed to harden before ejection from the mold. Virtually none of the feedstock is wasted because sprues, runners, and even rejects can be recycled for reuse. As molded, the part is an oversized replica of the desired part. Thus, shrinkage in subsequent processing must be accurately predicted. Debinding and sintering are performed in controlled atmosphere and under controlled processing parameters. Debinding is the process of removing the binder and can be by solvent extraction and heat or by evaporation. Either way, some binder is purposely retained in the part to maintain some green strength for subsequent handling. Sintering follows in a two-stage furnace. In the first stage, the remaining binder is removed at an elevated temperature. In the second stage, the part is sintered. During sintering, the part shrinks, removing almost all of the porosity. Total time for debinding and sintering can range from 8 to 24 hours or more. However, identical parts can be processed simultaneously increasing overall production rate. Powder consolidation by isostatic pressing at room temperature is called cold isostatic pressing, or CIP. When performed at an elevated temperature, it is known as hot isostatic pressing, or HIP. Cold and hot isostatic pressing applies high pressure to the powder uniformly in all directions, thus producing consistent density. The press for cold isostatic pressing includes a pressure chamber, pressure generator, depressurizing equipment, and machine controls. The powder is placed in a flexible, pre-shaped elastomeric mold, also called a bag, and consolidated by high-pressure water or oil. Pressures range from 10,000 to 70,000 psi, depending on the powder being processed. Dwell time at full pressure is a few minutes. The molds may be removable or fixed in the press. Removable molds are filled and sealed outside the press, then immersed in the fluid and pressurized. After consolidation and depressurization, removable molds are stripped from the part. This is called the WetBag process. Fixed molds are filled and sealed within the press, and the pressure is applied behind a membrane integral with the mold. The bottom closure lowers to remove the part after pressing. Because the fluid never touches the mold, this is called the dry bag process. After consolidation, parts are rarely net shape or near full density. These qualities are typically achieved in subsequent sintering, or, in the case of preforms, by forging and sintering. If made to net or near net shape and sintered, however, parts can be densified to nearly full density by hot isostatic pressing. A press for hot isostatic pressing consists of a pressure vessel, gas storage and handling system, a furnace, which is typically resistance heated, and machine controls. Powder is placed in pre-shaped sheet metal molds. Mild steel is the most common mold material. Others include austenitic stainless steel, titanium, tantalum, and copper. For complex shapes, the molds are usually welded fabrications of formed parts. Once filled, the molds are evacuated, sealed, and then assembled into fixture cans, which are lowered into the pressure vessel. The furnace is placed over the vessel, completely surrounding the molds, and sealed. Heat and gaseous pressure are then applied, consolidating and sintering the powder in a controlled atmosphere. Depending on the metal being processed, temperatures can range up to 2,500 degrees Fahrenheit, with pressures up to 45,000 psi or more. The gas, typically inert, is usually argon. Processing cycles are long, from several hours to more than a day. However, many parts can be processed simultaneously. After processing, the molds are removed by machining or chemical leaching. Dual metal parts can also be made by hot isostatic pressing. This involves diffusion bonding, or cladding a layer of dissimilar material to the surface of a base metal component.